Okay, once again, good morning, everybody. So we proceed with lesson 8 on hypothesis testing with t-test. This is where we start the real inferential statistics, and from there we move onward. All right, so what are you up to? What will you be able to do at the end of this lesson? You should be able to explain the logic of hypothesis testing, which we took this in 901, especially when it comes to the educational research. You should be able to differentiate between one sample, independent samples, and then peer samples t-test. And you should be able to state the hypothesis, the null hypothesis, both the null and alternate hypothesis for comparing means. Because basically, t-test has to do with comparing means, okay, of two groups. So it is a mean difference test. T-test basically is what? A mean difference test. So you should be able to conduct this using SPSS, and you should be able to interpret the output. And at the same time, you should be able to write the result of t-test in APA format, either in your abstract or in the body of your work, that is in chapter 4, or in your manuscript for publications. You should be able to report it appropriately using the APA 7th edition format. Excellent. So, the concept of hypothesis testing is all about the logic and the philosophy of falsification, which I think we spoke about this sometimes back, where we want to achieve the positive thing, then we assume the alternate, and then we test, and then we reject so in order to affirm what we wanted. So this is how it goes. So hypothesis testing is all about research-based prediction about the population parameter. So we have the population parameter which we want to predict from the sample. And this is the hallmark of every quantitative research. You have a small sample which your intention is to generalize to the population. So you want to move from sample to population. Or like in qualitative research where you don't do that, you don't need generalization. So in quantitative, what you do basically is to estimate the population parameters, okay, in which you'll be using the sample statistics. That's the point. You use the sample statistics to estimate the population parameters. I think we mentioned this sometimes back that we have statistics to the sample as parameters to the population. So take note of this. So basically, we hypothesize, right? Null hypothesis is a common thing we do, even though we can argue this, whether we should be using null hypothesis or we should be using the alternate hypothesis, and which one is actually the best. So this can become a debate. Hopefully, we have a time to debate that. So we have a group that we say they are in support of null hypothesis. Then we have another group that we say they support the research or the alternate hypothesis, and they bring their reasons why the hypothesis should hold and which one is better than the other. Of course, from a logical argument, not just from sentiment or how we used to do it. So null hypothesis is to assume no mean difference, all right? No main difference. There is no significant difference between the performance of this and that, between the attitude of this and that, between the motivation of this and that. There is no significant difference. Huh? So you are kicking out the possibility of significant difference. And then you make that assumption, and then you try to falsify that assumption. And that is coming from the philosophy of Karl Popper, that philosophy of falsification. This is different from the philosophy of verification, which they use a lot in biology, where you make your hypothesis, then you verify that particular hypothesis. According to Popper, you falsify rather than verify. In both ways, researchers, philosophers, they've argued a lot that even that falsification is another form of verification. In any case, so we have the null hypothesis that says no significant difference. Then we have the alternate hypothesis, which say, okay, there is significant difference. And this is a statement of affirmation, all right, which actually is in line with the theory. Because for every research, for every quantitative research, you need to have a theory that is backing up your study. Okay, constructivism lets you know that if students are given the chance to construct this knowledge themselves, they will perform better. All right? So there must be this difference as a result of using constructivist approach of teaching. So, and your job is to verify that hypothesis from the theory. Okay? So, and that is why alternate hypothesis is gaining ground. But when you say there is no significant difference, you are actually negating what you have affirmed in your theory. And this is the point. But in any case, we still stick to null hypothesis and we talk about them, we talk about it, and then we also talk about the alternate hypothesis. And what we do again after stating our hypothesis in the logic of hypothesis testing, we also set our level of confidence, right? The level of significance. So the alpha value, the amount of error we can tolerate, okay, in our research. So we usually fix 5%, okay? And that's why you see alpha equals to 0.05. People used to mistake this one for p-value. They are two different things. Confidence level is different from the p-value. Okay? The p-value is about the probability. Okay, probability of doing what? Of obtaining the data given that the null hypothesis is true. You assume the null hypothesis is true, and then you want to know the probability of obtaining the data you've got. All right, but for the level of significance, it's the amount of errors you can tolerate in your research. Though we compare p-value, the probability value, with alpha value, which is the confidence level. All right, so you state your confidence level, alpha equals to 0.05, not p equals to 0.05. I've seen this in thesis of students where there are p equals to 0.05 significance level. That is wrong. It's not p, it's alpha. And you are comparing p value with that alpha value of 0.05. So technically, it's very important. So in medicine, and where they have some kind of stricter rules, they set their own error tolerance to be 1%. Okay, but in education, we still have 5%. All right. So after doing that, then you select the appropriate statistical test. And this selection of appropriate statistical test is very important. If you are talking about mean different tests, of course, and you have two groups, we talk about the parametric or non-parametric test. This is very important when it comes to selection of appropriate statistical test. You don't just pick it from nowhere. It must come from the behaviors of your data set. If your data set satisfies the hypothesis of the assumptions of parametric test, then use parametric test. And at the same time, if your data set does not satisfy the assumptions of parametric test, you use non-parametric test. And these assumptions are testable. You don't just assume them and you move. You do what? You test for these assumptions. All right? So the result of your hypothesis assumption testing will now determine whether to use parametric test or non-parametric test. I can see some students are raising up your hands. Maybe it has to do by mistake. So lowering your hands now. All right.
No mistakes, sir.
Okay, please. If you want to speak, then you can just unmute yourself and speak. There is no problem. You can
All
interrupt me.
right, sir. Thank you
Go
very
ahead.
much, sir. Yes, as you are explaining, talking about the criteria that will warrant you to use parametric and non-parametric statistics, actually draw my attention because I'm actually having concern to that angle. So, please, I don't know if you can actually help us give us the basis or the param or what we will look at for in our hypothesis to be able to help us identify that whether we're going to use parametric or non-parametric statistics to test our hypothesis, because I'm actually having concern in that angle to actually know, okay, this one goes for non-parametric and this one goes. So what are those things I will look out for in my hypothesis to be able to make that kind of informed decision on this and the nature of the hypothesis to use for my testing? Thank you, sir.
All right, excellent. So I see, let me just give you the principle. The principle is this: generate your data set the way you have generated your data set. And then on the type of statistical test to use, the very first thing, we have said it in this class, the very first thing you do is to explore your data set, which we call the data exploration. So in the exploration of a data set, you will check whether there is excess skewness or there is excess kurtosis, or whether your data set is normally distributed. All right? This is the major thing when it comes to the hypothesis choosing the right statistical test, the normal distribution. Because for other assumptions of parametric tests, they are naturally satisfied. Like for instance, when you talk about the independent sample, of course, when you have two samples, you have already satisfied that assumption. Or when say you have continuous data set, when your variables are measured at either interval or ratio. So you also have that naturally by how do you identify your variables from the instrument? How do you generate your data? So then talk of the equality, I mean equality of variance. That one, any t-test will give you that result, and we even give you double result whether the assumption of homogeneity of variance is satisfied or not. So you don't have much problem on those other hypotheses. But for that of normality, you need to subject that to test by exploring your data set. So that's why we emphasize more on that. So you can use and in the last class we demonstrated how to check for the normality test, the normality assumption. We spoke about the Shapiro-Wilk and the Smirnov-Kolmogorov, right? You remember that. So that data exploration will tell you whether your data set is normally distributed or not. If your data set is normally distributed, then you have to choose parametric test. Okay, and if your data set is not normally distributed, then you have to choose non-parametric test. Remember, we are talking about continuous variables here. If your variables are categorical, of course you have to look for chi-square or some other logistic regression also to do that one. But if it is continuous, like we used to have motivation, attitude, name them, so performance, also anxiety, these are all continuous, the way we measure them. Okay, take note of that. Because we usually measure them by adding the scores together, converting the initial categorical to continuous. So in this case, just check for normality. If you check your normality, if it is normally distributed, good and fine, use your parametric test. If it's not normally distributed, then go for non-parametric test. As simple as that. Somebody's asking me about the data view in SPSS. When we get to the demonstration now, I can answer that question. Take note of that. Okay, so I think we are good to go. And there is this misconception, very important. I need to mention this now. People have this thought that okay, when you are dealing with performance, then parametric test. When you are dealing with attitude, motivation, or other psychological variables, non-parametric test. That is extremely wrong. Absolutely incorrect. It's not. So you don't say, because this is performance, I must use parametric. Because this one is motivation, I must use what? Non-parametric. That is a big misconception. It's a big wax, right? So it's not right. So what will determine whether to use parametric test or non-parametric test is the outcome of your data exploration. If your data is normally distributed and you satisfy all of the assumptions naturally, use your parametric, otherwise non-parametric. In fact, performance can be normal at times when you have to use non-parametric test, even for performance. So take note of this. I'm seeing when Abu Usman consistently raising his hand. You can unmute yourself and speak if you want to speak. All right. Maybe it doesn't. Perhaps that is coming from a problem, a mistake from, yeah. And also there is this suggestion that we also have some videos on Educate 01 where we explain some of this thing. You can refresh your memory. I have the videos there on my YouTube channel, so you can refresh your memories by going through some of these videos. So you enjoyed those videos. All right. So then we select the appropriate statistical test. I think I just mentioned that. And for today, we are focusing more on t-test. All right. So where we set our p-value and we compare with alpha. Take note, we have p-value being compared with alpha. Whatever p-value we get from the output of SPSS, we compare with alpha value. And remember, alpha is always what? 0.05. If our p-value is less than alpha, we'll reject the null hypothesis. Okay? We'll reject remember, null hypothesis, there is no significant difference. So when you reject that, okay, what does that mean? Maybe that is another big question, and there is a fallacy in there too. Okay, a lot of statistical misconceptions. We will try as much as possible to clarify them as we move on. Then if p-value is greater than or equal to 0.05, then you fail to reject the null hypothesis. Okay, the question now is this: when you reject the null hypothesis, what does that mean? What does it mean? So in the simple term, when you reject the null hypothesis, it is telling you that you are claiming, or you have some kind of evidence to argue that the data you get is not due to error. Look, the obtained data, the obtained result, is not due to chance. You have given an intervention on motivation. okay, or on motivation. And then after your intervention, you discover that you have to reject the null hypothesis. Okay, so that means that you are rejecting the what? The null hypothesis. And by implication, it means that the result you have got at the end of your experiment is not due to chance. That is the only thing p-value will tell you. But the question is this: the result is not due to chance, right? Does that necessarily mean that the result is due to your intervention? This is a big question. If the result that you have got after the intervention is not due to chance, it's not due to error or disturbance, random error, it must be due to something, right? That thing that it is due to, is it your intervention? And that is a gap there. And that is why researchers will tell you, or psychometricians will tell you, when you reject the null hypothesis, it does not necessarily affirm the alternate hypothesis. And that's why you have to go back to your design. So your design will now be the one that will give you the leverage to claim that result, okay, as an outcome of your intervention. And that's why we advocate for some strong designs like quasi-experimental or purely experimental. Because through that, you would have removed all other variables, the confounding factors, and then you have rest of mind to claim that, oh, this result I've got is as a result of my intervention. P-value will only tell you that result you have got is not due to chance. Is it due to my intervention? The answer is yes or no. It is yes if you take care of other factors that could lead to that outcome through your design, through the validity and reliability of your instrument. So take note of this. This is very important when we talk about this. Then again, we make our decision, and then when we fail to reject the null hypothesis, oh, so it could lead to chance. So that means my experiment is meaningless, kind of, because this thing can be due to chance. All right. Then again, we talk about the overview of the t-test, the type of t-test we have. I'm right here, so I just have to switch over the light so that we have enough brightness. All right. So as I'm saying, then we have the overview of different types of t-tests we have. We have the one sample t-test, so where we have a sample and we are comparing with a standard, okay, a benchmark. All right, like in our 901 class, if you remember this, there was this joke about New Bamali Polytechnic where the lecturers there are being paid lower than the minimum wage. So we can get the sample, we can interview some of the lecturers and ask them of how much they are getting, and then we compare that. That's a single group. We compare that data set we get against the national minimum wage of 70 or 72,000 naira that the government approved. So that's for one sample. While for independent sample t-test, we also have independent sample t-test where you are comparing means of two unrelated groups. All right, means of two unrelated groups. So you use the independent sample t-test. When you have two groups and then you are comparing the means of these two groups, then you use what? Independent sample. And you have the paired sample t-test. So that's when you have two groups and you test them two times, for instance. So you have a double scores. All right. So I need to mention one or two things here. You see, for independent sample t-test, we say how many groups? Two groups, right? But if your design is pre-test, post-test, take note of this. If your design is pre-test, post-test, that means these two groups of students, you must have given them pre-test before your experiment and then post-test after your experiment. It makes no statistical sense and practical sense for you to go to the post-test and then use t-test. You forget about the pre-test you've given to them. That is not your design. Because the pre-test, we let you know the differences before the experiment. All right. So by the time you go to post-test and you just do t-test without accounting for that initial differences, you are making a serious error. Because the result you get, if you use t-test at the end, the result you are going to get, you can hardly ascribe it to your intervention. Now, if the t-test tells you that there is significant difference, that difference you have got now, the question now is this: Is it due to your intervention or due to initial differences before the experiment? Take for instance, here in Zaria, I'm using two groups, okay? I pick my experimental group to be demonstration, right? And I pick my control group to be GSS Amaru, right? I give them pretest, but I don't use the pretest. Between the performance of demonstration and Samaru, we infect, we do what? We infect the outcome. So you cannot comfortably say that the difference you have got has to do with your intervention because the initial differences will mess up that result. So that is why whenever you're using pretest, post-test, cross-experimental, the result of the pretest must be incorporated. Even though you have two groups, right? Must be incorporated in the analysis of post-test. And that is what ANCOVA will do for you, which t-test can never do it because t-tests don't have the capability to look at history of your participants. So be careful here. Two groups does not necessarily mean t-test. If there is history, you cannot use t-test. You have to use a higher statistic, which is an ANCOVA that can take care of that history. Okay? And for peer sample t-test, two groups, related groups. Then use what? But even those two groups related, if you have something else that can confound the the outcome, then you have to incorporate that into your analysis or post-test. Take note of that. All right. So how do we now conduct t-test? One sample in SPSS. A one sample t-test is appropriate, or when can you use it? When you have only one group of participants, right? And then you are comparing the mean. Remember, t-test is all about what? Mean difference. You are comparing the mean of that your sample data set or your sample with the population mean or the expected population mean. Okay? So like for instance, the example I gave where you are comparing the salaries of lecturers in Ubamali with the national minimum wage, or you are comparing the mean test, scores of your students with the national benchmark. Maybe JAM said that the cutoff mark for admission into universities is 140 marks. All right. So you want to know whether the student in your school, you are the principal, you want to know whether the student in your school, their scores are significantly different from the national minimum cutoff, or their scores are not significantly different from that. So you can use t-test. Just arrange their scores, then compare with the national minimum. Okay, which we are going to do now. All right. So look at this one. The SS2 students significantly exceed the national benchmark of 50% in mathematics. Right? So you can state your null hypothesis. Their mean is the same. There is no difference between their mean and the national minimum. You know, when you bring this 50 to the other side, you have mu, that is your mean, minus 50. All right? So, and that is the difference, which is going to be 0. And that's why we have there is no significant difference. Okay, and the alternate is what? There is significant difference. But I mentioned the last time, rejecting the null hypothesis is not affirming the alternate. Rejecting the what? Null hypothesis is not affirming the alternate hypothesis. This is very important. Write it down. Rejecting the null hypothesis is not affirming the alternate hypothesis. Rejecting the null hypothesis only tells you that that result is not due to chance. For you to affirm the alternate hypothesis, you need to go beyond statistics, go to your design, go to the validity and reliability of your instrument, and that's why you must be careful. So take note of that. So let us run this simple analysis. We have our SPSS. You open your SPSS. I'm almost here already. Then we are using this test score. You have this already and is in your Google Drive. So when you open this test score, remember how we do this? Somebody was asking me about data view or variable view. So this is where you go to it. At the bottom here, the bottom left corner, so you have variable view, you have data view, variable view, data view, all right? So you come to variable view, we have gender in the data set. When you come to value, you can see we have 1 for male and then 2 for female. And we have the math score of the student, and then you have the reading score of the student. So we want to know whether this their math score is significantly different from the national benchmark of 50, the mean of the math score, whether or not it is significantly different from the national benchmark of 50. So you come to analyze. This is where you come to do it. And then you come to compare means, very simple thing. Then you pick one sample t-test. All right, I repeat, you go to analyze, compare means, then you choose what? One sample t-test. Do you get it? So you click on, oh sorry, I've just taken independent there. So analyze, then one sample t, then it comes here. Then that's your mathematics score. You put it as a test variable, and this is where you now put the national benchmark. You see it now. The national benchmark is what? 50. That's a national benchmark. 50. Then you click on OK. That's all you need here. So when you click on OK, then you have this output, this beautiful output. So in this output, you have the math score, the number of students. We have 100 students. The mean is 69.12. That is the mean of your sample. And remember, the national is what? 50. The standard deviation is 7.586, and the standard error of the mean is 0.759. Then you now come to the one sample t-test table. The test value is 50. That is the minimum benchmark. Our t-value, this is your t-value, is what? 25.20. Degree of freedom is what? Is 99. Then the p-value is what? 0.000. Right? In which we have said this before, in SPSS, when the output is 0.000 and you are reporting it, you have to say p is less than 0.001. Okay? P is less than what? 0.001. Because this 0 you see here is not actually 0. If you extend the significant value, it goes 0.0000000.2 or so point something. It is not actually 0. All right? So take note of that. Then the mean difference between your sample and the national is 19.117. That means if you subtract 50 from 69.12, you should get this one. Then this is a 90% confidence interval, then you are okay. So with this now, we can see our p-value is less than 0.001, which is actually less than 0.05. All right? So that means we have to reject the null hypothesis. We have to do what? Reject the null hypothesis. And then we conclude that our student, they actually the mean of our student in mathematics is significantly different from the national mean. All right. So take note of this. Remember, we are working on the premise that we have already looked at this data before, and we found that this data is what it satisfies the assumptions of parametric, because t-test is parametric. Okay. Then we move on. So we have sample output. I think we should get the same thing if I'm not mistaken. I think I did it before. So with the same output. So, and we have just interpreted this output. And if you want to use the syntax to do it, this is the syntax code. You want to use the syntax. But we say in our last previous classes that we'll be focusing only on the graphical user interface. And for those who are more interested in statistical analysis, they can try the syntax and use that. So, of course, we just mentioned this. If p-value is less than 0.05, we reject the non-hypothesis. And then we conclude that students perform significantly different from the benchmark. Okay? Very good. So, and this is how you interpret and even report it in APA format. Look, a one sample t-test showed that the mean mathematics score of SST student, you put the mean and you put the standard deviation in bracket. This is the standard. Okay, you put the mean and the standard deviation in bracket, was significantly higher than the national benchmark of what? 50, comma, you put t-value and degree of freedom in bracket, and then you put the t statistic. Look, this is t, degree of freedom equals to t statistic, comma, p is less than 0.001. Remember, our p is 0 from the SPSS output. So we're gonna write p is less than what? 0.001. So this suggests that students in the sample perform above the expected national level. So this is how you write this, and in your abstract or in your chapter 4. Look, we have reported this result in 2 stages. Number 1, we reported the statistical result. Okay, And this is how a standard abstract should be written. You report the statistical result, then you let your audience know what the statistical result actually mean. So you report the statistical result and then you interpret it. So this is statistical result, okay? And then this is what? Interpretation. If someone is deficient in reading statistical result, at least the plain statement here should be readable, isn't it? So you can see in this interpretation, there is no use of any statistical term. Take note of that. Okay, so this is the basic things you need when it comes to one sample t-test. Then we move straight to the independent sample t-test. And when do we use it? So when we have two independent groups, all right, experimental and control, which are not in the same school. Okay. Then we have the dependent variable that is continuous or interval, and then the independent variable will be categorical. Right? Remember, the dependent variable must be what? Continuous. Performance, you want to know the impact of inquiry-based learning on student performance in chemistry. Impact of what? Inquiry-based learning on student performance in chemistry. Okay, then I have two groups of students. I taught them using one group I taught using inquiry-based learning. The second group I taught using the conventional method. I collected their performance at the end of the experiment. Then I want to compare the mean difference in the performance. I want to know which of them is having a higher statistical significant difference in their means. So in this case, the performance is continuous. How you measure it? Not just performance is continuous. Performance can be categorical. But how you measure performance will determine whether it is continuous or not. Take note of this. Okay. Like GPA now, degree classification, first class, second class, third class, these degree classification, they are coming from performance of the student or achievement. And first class, second class, upper, second class, lower, that is categorical. The same thing is grades of your student. A, B, C, D, E, F. It is categorical. And the grades are coming from performance. And you can have high performing and low performing. Okay? Where you have two groups at the end of the day. So how you measure your performance will determine whether it is continuous or not. This is very important. So, but now we are saying that we have measured the performance here using the addition of scores to get a composite score for each student. And so it is continuous. Very good. Then the independent variable, inquiry-based learning, okay, and then we have the conventional method. The two of them, they are talking about one thing, which is about method of teaching. So our independent variable is actually method of teaching. You can make a mistake by saying independent variable is inquiry. No, independent variable is not inquiry-based learning. Independent variable is what? Method of teaching. So this method of teaching, it has two levels. Inquiry and then conventional. That is categorical. So that's why we say that independent variable should be categorical. And that categorical must be two levels before you can talk about t-test. If you have the levels to be 3, you cannot use t-test. Take note of that. And you can still use it, but it will not be the best practice. You'll be inflating your type 1 error. Take note. So look at this. Is there a significant difference in mathematics achievement between male and female? Now we have two groups. The males and then the what? The females. So gender is the only independent variable here. And that gender is having how many levels? 2 levels, male and female. You want to know the performance, the difference in their performance. Okay. So our hypothesis, our null hypothesis is going to be there is no significant difference in mean mathematics achievement between male and female students. And the alternate is there is significant difference. And we have mentioned before, don't make that mistake. When you reject the null hypothesis, you don't necessarily affirm the alternate hypothesis. Very important. Excellent. So how do we now run this in the SPSS? We go back to our data sets. Here we are. So this is our data set. We are still using this particular data set. Remember, this is what? This is the scores of the student in mathematics. And then here we have the gender, male or female. Okay, let me check the charts. Okay. Okay, somebody's talking about the sand. That must be from your hand. Thank you very much, that person that responded. All right, so we are saying that the gender, this is your gender, and one is for male and then two is for female. We want to know the gender difference in the performance of student in mathematics score. Okay, so this is typical example where t-test is a perfect thing. You know, we don't talk about pre-test here. We only have one score, and then for both male and female. So you come to analyze, and then we come to compare means. Again, this is where you do your t-test. All your mean difference tests and analysis of variance, they're here. Then you come to independent, you know, we just did one sample now. You come to independent sample t-test. Then you click on that. Then you have this dialog box. Okay? Your test variable, that is your dependent variable, you put it in your test variable. Okay? And then the gender of the student, which is your independent variable or the grouping variable, you put it here. Then you see question mark. It means I have to define this group. So you come to these defined groups. What you have in your group, gender, you have one for male and then two for female. So you have group one for male, put one there, and then you have group two for female, put two there, and then you click on continue. You see this now. So then you run your. There is nothing much here. You just need to don't bother about this, and forget about bootstrapping. This one is a different thing we talk about if you have the chance. Then you click on OK. Then click on OK. So when you click on OK, you have this interesting table coming at you, pumping to your face, right? So here we have it. So we have the descriptive statistics, which you need. Descriptive what? Statistics. And then you have your male, 60, your female, 40. You have the mean to be 67 for the male, and then the mean for the female is 72.09. Standard deviation are here and standard errors are here. This one you can report it in your addressing the search question if you like. Then you come to, now you remember I said that one of the assumptions of parametric test is what the homogeneity of variance. So you can see the output of t-test is having already homogeneity of variance. So you don't have to worry your head about testing this. Whether you assume it or you don't assume it, the results are presented. Now, when we assume that homogeneity of variance is true, then this is a Lebanese test to tell you, in fact, it's true. Okay, and then this is your t statistic, and this is your degree of freedom. Okay, and this is your p-value. You see it now. So mean difference and some other things you need are there. And if we don't assume the homogeneity of variance, the report it is still telling us that the p-value is less than 0.05. So because p-value here is exactly 0.001. So that means we have to reject the null hypothesis. Okay, and affirm that our result that we got is not due to chance, it must due to that gender difference. Okay, all other things being equal. All right, so and this is where we come back to our note. And if you want to do this using syntax, I put the syntax here, and here we have the same result, the same output from our SPSS, and then since our p is equal to 0.001, which is of course less than 0.05, we must reject the null hypothesis, and we conclude that there is statistically significant difference between male and female student performance in mathematics. So, and in fact, because females are having higher scores, higher means, that means they outperform the males. And I think this is becoming true these days, that females are becoming smarter than males in mathematics. Yeah. Okay. The assumptions, we said we have to check the assumptions parametric test, isn't it? But we have this particular data set which we've already checked the assumptions from our previous classes, and we know that this particular data set is normally distributed and satisfies every other assumption. The first one is about the continuity of the what? Of the data set. Yes, continuous, and it is approximately normally distributed. And the groups are independent. Of course, males are different from females, and we are not in a confused state in Nigeria where we have males that cannot identify as either male or female, right? Some say they are both of them, right? So, but we don't have that category. We have categories for male student and the data for female student. Then variances are equal. This is another assumption of parametric test, and I said you don't have to worry much about this, because SPSS will give you whether you assume it or you don't assume it. Okay, so you have your leverage here, and then what again? These are the basic three assumptions we need. There are four, but I wrote them in three parts because the first one can be split into two: continuity and then normal distribution. Okay, All right, so that is the basic things we need to look at when we speak about the independent sample t-test. Let us just play around again. Let us play around with that of the reading. You want to know again whether the reading performance of students on reading has to do with gender or not. So let us do that. So we come to compare means, then we come to again independent sample t-test. Instead of our math now, we remove the math score and now we put the reading score. As simple as that. Our grouping is remaining the same, then we click on OK. So when you do that, you have the outcome. You can see the reading, we have male to be 67 and the female to be 65. They are very close, but yet we don't know whether significant difference exists. Now, but come here, your t-value is now 1.692. The degree of freedom is 98. Then look at your p-value, 0.094. This is greater than 0.05. And by implication, it means what? You fail to reject the null hypothesis. You fail to reject the null hypothesis. That means there is no significant difference in the performance of male and female in what? In reading. But in mathematics, yes. In reading, no. So take note of this. Very important. Now we come to the last part of the notes, and which has to do with the paired sample t-test. Paired sample. This is when you give pre-test and then post-test for the same group of students. Like in the case of one group experimental research. You don't have the money, you don't have the permission to give different treatments to the different groups of students. Okay? You only have one group. So you give them pre-test, you give them what? Post-test. And then you compare their pre-test and post-test to see whether there is any change, which can be ascribed to your intervention. That is one group experiment. Some people will say one shot experimental research. So this one is used when we have participants that are measured twice. Okay, and you can also use this scope for retention too. You can use this for retention. That is between post-test and post-test. So example, does the use of virtual labs significantly improve students' chemistry performance? So you only have a classroom and you only have a single provision for virtual laboratories. So perhaps you are a teacher and you want to demonstrate the effect of a virtual lab on your student. Okay? So you only use your student. That is the only people you have. So you can do one group experiment before and after. We give them pre-test, maybe on performance, on motivation, or on attitude, and then give them post-test. Okay, after your intervention, after a semester or so, then you compare their pre-test with post-test. We did something like that recently when you look at the artificial intelligence literacy among our students. We modify a new course and then we ran the course on AI. So before the semester, at the first week of semester, we gave pre-test. At the end of that semester, we give them post-test. And we are comparing the difference in their performance on AI literacy before and after, and on some other variables too. So you can do that when you only have access to one group of students. So in this case, you'll be saying there is no significant difference between pre-test and post-test. And then the alternate will be there is significant difference. Something I must let you know here is that if you are going for this type of test, your pre-test, you must be able to identify the pre-test with the post-test for each student. Student A pre-test must be identifiable with student A post-test. Student B pre-test must correspond with student B post-test. That is how you must arrange your data set. So take note of that. So we can take a look at a data set which we have to open now. We are not using this. We are tired of reading and mathematics course. You open a new data set, come to data set, all right? Then you check chemistry pre-test and post-test. This data set is already in your Google Drive. So this is what we are using, chemistry pre-test and post-test data scores. So then you click on OK. So this is what we have. So you can see how the scores are arranged. This arrangement is different from independent sample t-test arrangement. So you can see we have two columns, right? Pre-test, post-test. Each of them, the pre-test of this guy is the same. This is the post-test of this corresponding guy. The pre-test of this one, this is the corresponding post-test. This is how it goes up to the end of the student in that class. There are 50 students in the class. So we now want to know whether there is significant difference between this pre-test and post-test. So we come to analyze again. Then we come to compare means. And then we come to paired samples t-test. This is where we do it. and then you bring your test variable. Usually I like putting post test as the 1, then click on this and then take it there as 2. So this is what you have. Post test is coming as variable 1 and then pretest is coming as variable 2. You can change the order, no problem. The only difference is that the sign may change if post test is higher than pretest. So anyway, it will not work for you. So but what you must do is that the peer 1, the post test must correspond with what? With pretest. You have options to compare more if you have more than one group. So you can compare pretest and post-test in reading, pretest and post-test in chemistry, pretest and post-test in mathematics for the same group of students. So there is nothing much in the options, so you don't have to worry much about this. Then you just click on OK. Then you see the outcome, the output coming out to you. So you can see post-test, we have 67.9, then pre-test, we have 53. So before the experiment, the mean performance of your students is 53, okay? Why after the experiment, the mean performance is what? Is 67. So you have 50 in group 1. Of course, there is no demo range. At times, you can have differences. Maybe some student didn't meet up, they drop out or something like that, or they didn't come when you are giving the post-test. Okay, the standard deviation are here and so on. Then sample correlation is given to you. So you have the sample correlation to be 0.109. You don't need this when you are reporting peer sampling test in your research. So now what we have, this is where we come. This is where we do things. So you have post-test minus pre-test here. That's the first pair. The mean difference is 14. The standard deviation is this. Standard error is this. Then you move on up to get to your t-value. Your t-value is 10.737 and your degree of freedom is 49. Remember, the degree of freedom for peer sample t-test is n minus 1. I repeat, the degree of freedom for paired sample t-test is what? N minus 1. N is 50 minus 1, that will give us 49. While for independent sample t-test, this one you have two groups. The first group we have N1, the second group we have N2. Okay, so the degree of freedom will be N1 plus N2 minus 2. N1 plus N2 minus 2. That's for independent sample t-test. For one sample t-test, it is N minus 1. Degree of freedom is what? N minus 1. I think we still have our output here. We can confirm what I'm just saying here. Look, we have, this is independent sample. 40 in group 1 and in group 2, then 60 in group 1. So N1 is 60, N2 is what? 40. N1 plus N2, that will give us 100. Minus 2 will give us 98. That's why the degree of freedom here is what? Is 98. Okay? N1 plus N2 minus 2. Why for one sample t-test, the degree of freedom is N minus 1. N is 100. Look at it. And the degree of freedom is what? 99. So N minus 1. So this is very important when, these are just some theoretical things that we should have covered in 901 or 801 or 802 as the case may be. All right, so now let's continue with our interpretation of the result. We have our t-value to be this, right? Degree of freedom to be 49, and then our p-value to be 0.000, right? So which I said, whenever you see this, don't report this in your table in chapter 4 or wherever. This doesn't make sense, okay? Rather, you put in your table in your chapter 4, p less than 0.001. I think that is the requirement for APA 7th edition. That's what APA is talking about. It's not just coming from my end or from what I don't like. It is coming from APA format. Take note of that. So what we can conclude here now, since our p-value is less than 0.05, we conclude that what? The main difference is what? Statistically significant. So that means, after my experiment, my student actually, they perform better. Now the question is, that performing better, is it as a result of my intervention or as a result of other factors? Maturity, other, maybe some student went to lesson, or they just like me because I'm the new teacher, or they like whatever. So a lot of factors. So your design will now allow you to conclude that yes, your result is as a result of your intervention. So this is very important when you're interpreting. You have to don't be too excited that you've got p-value. That means I have the best intervention and it is practically okay. It is very valuable. No, it's not so. It's not so. The p-value only tells you that you are knocking out the chance. You are knocking out the errors. But after knocking out the chance, what remains is that your intervention or something else. So that's where it is very risky. All right. So, and if you want to use the syntax, you can use it here. And I still repeat the same thing. You reject and then you accept. And then the output, I think I've explained that, but I didn't put it here. Another practical example, which I don't think I'm going to walk through this, you can walk through it yourself, is about effect of AI-based learning tools on student problem solving in secondary school mathematics. So you have the pre-test, you have the post-test, and then you can do your peer sample t-test and enjoy in peace. I'm not sure if I put the data set, I don't know, but the report, the output, and how do you now how do you report? How do you report independent sample t-test and then the paired sample t-test? So you can enjoy this CBT too. It's very interesting. You can enjoy that. And then I should have skipped this first. Let me skip this first. Let me go to reporting. So this is how you report the independent sample t-test. Okay. So in your chapter 4 or in your abstract, chapter 4 under the table, abstract, in the body of your abstract, you want to report independent sample t-test. You say an independent sample t-test indicated that female students scored significantly higher in mathematics than what? Than the male students. Okay? So you write your mean. Okay? Remember the mean for females is written here, standard deviation. The mean for males and standard deviation. Then t value into bracket, t into bracket, degree of freedom, and then the t value, and then the p value, and then the effect size. Okay, I think I now see the reason why I put this at the end, because I put the effect size. Okay. So why for the peer sample t-test, you also report a peer sample t-test revealed a significant improvement in student chemistry achievement from pre-test at the beginning to post-test at the end. You can see how it is going. T into bracket, degree of freedom equals to the T statistic. P is less than 0.00, and then the effect size is here. Then the intervention is effectively enhancing performance. So this is what you have here. So now I'm reporting one DD here. That is the effect size. That is what? The effect size. And this is very important. You see, when the p-value tells you that it's statistically significant difference, statistics is, let me say this, statistical significance is different from practical significance. I repeat, statistical significance is different from what? Practical significance. P-value will only tell you statistical significance. But if you want to know the practical significance of your intervention, you need to look at effect size. You need to look at what? Effect size. So effect size will be the one to give you the practical significance. As for statistical significance, p-value will give you that. And both of them are different. Results can be statistically significant, but it is practically irrelevant. It is what? Practically irrelevant, but it is statistical significant. So take note of this. This is very important. They don't mean the same. P-value is not telling you about the practical significance. For you to know or have an idea about practical significance, you need to go beyond p-value and go to effect size. Take note of this. Excellent. Okay, so the effect size, how do we get effect size for t-test? Okay, so this one is for, the formula is there for independent sample t-test. Okay, where you have the mean difference divided by the pool standard deviation, which is the pool standard deviation you can calculate in this formula. This is coming from 801 for those of you who took 801 with us. So then how do you now interpret? This is Cohen-D effect size. If it is 0.2, then it is small effect. If it is between 0.2 and 0.5, it is what? Medium effect. And if it is between 0.5 and 0.8, it is what? Large effect. Anything less than 0.2, it is practically irrelevant. Take note of that. Okay, so yeah, so and then when you do that for that male and female mathematics, then you get 0.63, which is in this range, large effect. Okay, but unfortunately SPSS doesn't give you this statistic, this effect size. SPSS will not give you, so you have to manually calculate yourself, or you do some kind of online statistical consultant or whatever, where you have some website that you can just put your mean, put your standard deviation, then it will calculate this thing for you. There are some free websites that can do that for you. Even t-test, there are some websites that will do it for you, and you'll be happy. Okay, so what about the good practice? And then for the paired sample t-test is just the difference in the mean divided by standard deviation. I'm not sure if I put it here, but that is just it. So, but some of you that took 801, or you watched the videos on effect size on Educ 802, we have the videos on the YouTube channel. You can watch that, and you'll be happy with yourself after doing so. All right, so then some practical good practices that we should imbibe when we are dealing with t-test. Okay, so one, you need to check your data set for normality or outliers and remove all these things that may pollute your result. So because violations may affect the accuracy of your result. Always report both p-value and the practical significance. See that now? Always report this. Always report your p-value, which will tell you about the statistical significance, and then the effect size that will tell you about the practical significance. So this is very important. So this will enhance your interpretation. This will let us know that you actually know what you are doing, not just following the crowd. Okay, then you have to use the appropriate t-test. Okay, you have to use appropriate t-test. So you are using paired sample, or you are using independent sample, or you are using one sample. So you don't have incorrect conclusions. And then you present your clear tables and contextualized interpretations, which can improve the clarity in thesis or manuscript publications for journals. So this is very important when you report nicely. Follow the APA format, which is the standard we follow in social sciences. So follow the APA format, look at how they say you should report it, and then you'll be happy while doing so. And yet you have less brutal comments from the reviewers. Okay, then report test assumptions. This is very important. You have to report the assumptions. So you need to justify why you are using independent sample t-test. The assumptions of parametric must be met. You need to justify why you are using paired sample t-test. The assumption of parametric must be met and the samples must be related. So you need to justify. And if you are not using this parametric test, non-parametric test, you need to justify why you are doing so. So, and then I think at this point we are okay, we are good. And then we just reported this with the effect sizes and the temperature of the large. So I have some kind of hands-on attacks here for you. You can enjoy yourself with this when you have the time. So, and I think you have a data to use also, so you'll be happy with yourself. And if there is any comments, questions that you have, you can let me know either in class or outside the class if you catch me. So I think at this point,